Hello everyone, I'm Prodromos Kolivakis and I would like to present you our paper called Geometric Algebra Meets Large Language Models that enables instruction-based transformations of separate meshes in 3D interactive and controllable scenes. This work is done jointly with Manos Kamarianakis and George Papalianakis at Orama VR and the University of Crete. And it explores how symbolic geometry and language models can jointly drive intuitive controllable 3D scene editing. 3D scene editing nowadays is still manual and expert heavy. State-of-the-art solutions like NERVs and Gaussian splatting have advanced really, but they are still holistic. Their objects are fused into one representation, so it's very hard to move a single item. Our goal is to combine the intuitiveness of text commands with the geometric precision of formal math, while working on separate editable meshes. So what is the problem that we are going to solve? Given a textual instruction such as place the orange bottle on the tool table, our system must output the exact 3D transformations by means of translation, rotation, and sometimes scale, and apply them interactively in a scene. We're going to work with separate mesh scenes in Unity and the TDW environments, and we're going to exploit few-shot LLM prompting. In addition to this, we propose a lightweight collision avoidance manager that helps us maintain realism. We call our system Shenlong, and it is the product of LLM and Conformal Geometric Algebra. The language model, on one hand, helps us interpret the natural language, while on the other hand, CGA enables symbolic precise transformations. Basically, an LLM helps us convert user text prompts into CGA transformations. The LLM produces a composed operator M that fuses together translation, rotation, and dilation, which in the final step we have to decode to unitary parameters t, q, and d respectively. So why conformal geometric algebra? In his seminal 1872 Erlangen program, Felix Klein introduced the revolutionary idea that the geometry is best explained by algebra, asserting that algebraic structures govern geometric shape. CGA, in brief, provides a unified algebraic language for points, lines, planes, spheres, and motions. Rotations and translations are both rotors, algebraic objects that compose neatly. This avoids ad hoc matrices and makes geometric reasoning symbolic, which is perfect for LLMs to manipulate. Here is a quick overview of CGA. CGA extends 3D space with two extra basis vectors that let us represent not just points, but also lines, planes, and spheres in one unified algebraic form. A point or a sphere becomes a multivector. You can see the expression here combining position and radius. This unified form is what allows geometric operations to remain algebraically consistent. Motions like translation, rotation, and scaling are encoded as rotors, algebraic entities that can be multiplied together. So instead of ad hoc matrix math, we compose transformations symbolically. We apply transformations using the sandwich product. From this, we can extract translation, scale, and rotation directly, and the rotation can be converted also into a unity quaternion for real-time rendering. This symbolic representation makes it possible for an LLM to reason about geometry precisely, without losing interpretability or structure. How we pass from the CGA world to engine parameters. After computing the composed multivector M, we can apply it to a unit sphere C. The transformed sphere gives us the center, x, which corresponds to the translation, and the radius r that corresponds to the scale. Rotation is then recovered and converted to a unity quaternion. So everything the LLM outputs is grounded in geometry. Here is an overview of our system. We first replace object names with variables x1, x2, etc. to make it easier for the LLM to reason about the world. The LLM receives 5 few-shot examples of basic operations, including rotation, translation, and relations such as on top, next to, and one composition example. LLM outputs JSON formatted CGA rotors per object. As a final step, we perform collision correction using a local DFS search on a 3D grid to explore perturbation of the original solution to resolve the collision before applying the final transformations. And let's present also some details regarding the element prompting. Each object is represented by its axis-aligned bounding box. We exploit CGA's inner and outer products to compute positions and define planes. The LLM reasons symbolically and outputs a JSON of transformation. No code generation, only geometry. You can also see an example of the output of the LLM. Collisions are resolved through axis-aligned bounding box overlap checks with a small buffer zone. A bounded DFS explores nearby grid positions to minimize deviation while keeping results interactive. The overall algorithm runs for less than 1 second per operation. And here is our evaluation setup. We integrated the system into 3D World and Unity. All queries were processed by GPT-4 and there were few shot with only 5 retries per query. We compared against two baselines, an omniverse prompt which generates unconstrained JSON placements and a Euclidean prompt which asks the LLM to form explicit translation and rotation matrices. We built 10 diverse scenes using Holodeck, yielding 2,500 queries in total. We used 20 annotators that evaluated each output. Each query was judged by 5 annotators and we required anonymity. We used two evaluation metrics, the success rate and the LLM response time. The response time also includes the time of retries. Here are the representative queries categories across 5 complexity levels, from simple translations to global arrangements. As you can see, we have basic geometric transformations, multi-step reasoning such as move x1 up and rotate by 45 degrees, which is sequential transformations, relational reasoning, which are fuzzy, like move x1 on top, that requires some understanding, compositional fuzzy, that fuses together compositional and fuzzy categories, and finally what we call hard, that require global spatial arrangement. The next video demonstrates Shenlong performing edits interactively. And let's pass to the quantitative results. On the left, we see the figure that reports the accuracy over the three systems, and on the right, the measured latency. Our system achieved the highest accuracy and the lowest latency, significantly outperforming both baselines. It was particularly strong on compositional and fuzzy queries, confirming that symbolic geometry reasoning improves consistency. Interestingly, all prompts were significantly weaker on hard queries. Last but not least, on the simple queries, our system achieved 100% accuracy. So, what are the lessons learned? CGA's symbolic structure gives the LLM a stable geometric language, avoiding numeric drift. The system generalized from only 5 examples to complex relation instructions. And we saw that hard cases remain challenging because pure text sometimes lacks sufficient spatial context. So what are the current limitations of future work? Object semantics. As we said, we perform exact name matching. And in the future, we can define token and embedding space similarities. We can also exploit caching. For instance, if a specific query was already solved, we can cache the required transformation, and this increases accuracy and speed. We can exploit a multimodal top-down visual guidance for the collision instead of using merely a DFS search, and we can explore further modalities such as speech input, also geometric algebra trained LLMs, and more competent LLMs. In summary, Shenlong translates natural language into geometric algebra and delivers precise engine-ready 3D edits on separate meshes. It's accurate, efficient, and operates few-shot. Our takeaway: symbolic geometry is a powerful bridge between LLMs and 3D engines. This work was funded by the InnoSwiss Omni project. We also welcome the industry reader to our paper for further information. Thank you very much for your attention.